So today we're going to mop up with a set of related topics and dive deep into DNS. So there's a couple of sides to DNS that most people aren't aware of. And today we're going to take a look at both flavors or we're going to look at the two main components of what a DNS server does: resolution and advertising advertising a DNS zone as an authoritative role, either as a primary or a secondary server. Let's move right along. So we covered the packet tracer issues. All right, when we talk about sockets, we said that a socket was a combination of well-known server address. Usually there's a client and a server. A server is running a service or a process to offer resources or data. It's listening on a port for a connection, a given port, and the client is going to connect to the IP address of the server. It's going to choose a high numbered port, an ephemeral port, a port number that changes for each connection with each server. With each session, it's going to choose a randomly assigned port. So the server ports are well known. The client ports are randomly assigned. Is this ringing a bell for anyone? We covered sockets.
Yeah, sounds familiar.
Okay. In most cases, many client server sockets formed are either TCP or UDP. This is layer 4. This is in your study guide. And you may recall some basics we've mentioned along the way, that TCP/IP guarantees delivery. It's usually for important data files where you want to make sure everything gets there, like an SSL certificate when you're encrypting your connection with a website, or an email message that has to be updated to your mailbox, or a file transfer, a download from Microsoft, right? So TCP is guaranteeing delivery where important data files, the integrity of the data file is important. UDP does not. So in terms of IP connections, UDP is best for bulk and streaming content. So streaming media is a great example. Standard movies deliver 25 different isolated images to your eye when you watch a standard movie in a movie theater, 25 images per second. And if one of those images drops, if you drop one random image every second, so that only 24 make it to your eye, it's very, very hard for your eye to detect the difference. The same thing is true with audio. If I'm forming words with long syllables, and each of the bytes that's carrying my sound to you, drops a few packets along the way, it's not going to be noticeable unless I start talking very much faster, in which case, because the words are in much smaller chunks, that's more discernible. But the point is that UDP is often used for bulk delivery. TCP is designed for special delivery. TCP sessions are formed with reliable two-way connections using a three-way handshake, and this is really important to know. On slide 503 in your Comer slides, the student notes, basically it shows that three-way handshake. So there is a reliable, consistent, fixed connection. It's a two-way connection that's established with a three-way handshake, and UDP doesn't do that. Basically, UDP does not, it creates a session, but it doesn't create a persistent connection that's established with a three-way handshake for reliable delivery. Okay, so So there is a session that's formed between client and server for UDP, but it doesn't set up the same way at all. It's not a two-way connection that's persistent for reliable delivery. Okay, that's important to notice. That's going to come in. That's going to come in handy. That understanding is going to come in handy. I wanted to show you though the slide 503. So this is from Comer, right? And it's important to understand the steps that this follows when a TCP handshake is performed. It's important to understand this in order to be able to troubleshoot TCP connection problems. It's also important to understand this because hackers like to poke their nose in the middle of this process and commandeer the connection. So understanding this connection and the sequence of actions on both sides, right, is important. So you have a server that's running and a client sends a SYN pack. So host 2 is the server, usually. It's sitting there listening for a connection. And a client says, hey, is there a web page? Hey, is there email? Hey, is there a movie? Right? So they're going to make the first action and they're going to send a SYN packet to the server, and the server receives the SYN packet. And the first thing the server does, counterintuitively, is instead of acknowledging that and going, oh yeah, I've got a movie for you. I've got an email for you. I've got a web page for you. The server doesn't do that at first. The server says, oh, it sends a SYN packet. It's designed to help synchronize the connection. The host, the server that's receiving that first attempt says, oh, do I have a client? So, hey, is this a server where I can get email and web? Sends the SYN packet. The server goes, hey, is this a client that wants an email or a web packet or a, streaming content, right? And then it acknowledges, next, it acknowledges the, hey, I got your connection request, right? That's what SYN means. So on the other side, the host receives that SYN back. Hey, are you a client? And then it receives the acknowledgement. I received your request for a connection, is basically what it's acknowledging. And then the client says, yeah, that was me. It acknowledges that, yes, I am a client for email or web server or whatever. And on the server side, when that's sent back, it receives this confirmation from the client. So they're both checking each other out. They're both validating the fact that, they're each playing a role, they're each connecting for a certain kind of data. And that's what's going on here. You're going to get an assessment question where I'm going to ask you to order the steps of the three-way handshake, right? And in simple terms, it's SYN, SYN-ACK. So the first host says SYN, second host says SYN-ACK back at you. And then the original client says ACK back, right? So in terms of who's sending what, the SYN packet comes from the client, a SYN-ACK packet is sent back from the server, and the client sends a final ACK packet back. And at that point, then there are sequence numbers for each of the packets that flow back and forth. Now, the reason that three-way handshake is so important is because after that point, data packets start coming and they each have sequence numbers, and those sequence numbers help the client and the server order those packets in their proper order when they're received on the other end. Remember that packets can take different paths. They can each flow in different routes. And when they get to the other end, they might not be in the correct order. So the sequence number is important. That's one reason why we can guarantee delivery, because of the sequence number. This becomes vitally important for certain types of server transactions. You'll see just in a minute. Any questions about the three-way handshake that's used to form a TCP reliable connection? No questions? Is everybody there?
I'm here.
Okay.
I'm here.
All right. So moving right along. Today, we're going to explore more about DNS. We're going to explain DNS, how it works. We're going to contrast resolution and authoritative roles. We're going to revisit UDP and TCP with respect to DNS server function. Okay. So we're going to revisit this whole idea about the differences between those two layer 4 transport methods. And then we're going to retrace the steps that any system or device uses to find a DNS address. There's a specific process that it follows when it's trying to find a named resource out on a network. Understanding the steps that are used and followed to identify a named resource out on the network is most important because, well, it helps you both in terms of configuring DNS properly and in terms of simple problem solving. So our next objective is to describe DNS best practices, how you can make your network bulletproof, and then to perform simple tasks to resolve DNS errors, and then finally to design, implement, and test your own domain name. You're going to create a DNS zone in a live setting. And if you were Mark Zuckerberg about to create Facebook, or the guys that Jeff Bezos about to create Amazon, Jeff Bezos woke up one night and said, I'm going to call my domain Amazon.com. And Mark Zuckerberg said, hey, I think this application ought to be called Facebook. And it's, it's going to be commercial, so it'll be a .com, right? Not a Facebook.net, but a Facebook.com, because we're going to make a lot of money. And they created their domains and they set up a DNS zone, and everybody's been using those DNS zones ever since. I want you to be able to have the same capacity to create your own online resource to the scale that Jeff Bezos and Mark Zuckerberg actually did. DNS is powerful. And if you understand some basics about it, it can help you solve a lot of network problems. All right, so without further ado, let's look at how DNS works.
But since we are not accustomed to memorizing and dealing with numbers.
Can everybody hear the audio?
Yes.
Okay.
Especially when there are millions of websites on the internet, we can just type in the domain name instead and let DNS convert it to an IP address for us. So back to our example, when you type in yahoo.com in your web browser, the DNS server will search through its database to find a matching IP address for that domain name.
That lookup function is called resolution or resolving. So one of the functions of a DNS server is to do the lookup function, and it uses other DNS servers to conduct the lookup, okay?
And when it finds it, it will resolve that domain name to the IP address of the Yahoo website. And once that is done, then your computer is able to communicate with the Yahoo web server and retrieve the web page. So DNS basically works like a phone book. When you want to find a number, you don't look up the number first. You look up the name first, then it will give you the number. So to break this down into further detail, let's examine the steps that DNS takes. So when you type in yahoo.com in your web browser, and if your web browser or operating system can't find the IP address in its own.
Okay, so the process that he's about to tell you about is called recursion. Think of the term recursive in programming. Recursion. DNS recursion is the heavy backend work that's done when someone's looking up a new domain for the first time and they can't find it because it's brand new. Okay, so we're going to pretend that yahoo.com is brand new.
In cache memory, it will send the query to the next level to what is called the resolver server. The resolver server is basically your ISP or internet service provider. So when the resolver receives the query, it will check its own cache memory to find an IP address for yahoo.com, and if it can't find it, it will send the query to the next level, which is the root server. The root servers are the top or the root of a DNS hierarchy. There are 13 sets of these root servers, and they are strategically placed around the world, and they are operated by 12 different organizations. And each set of these root servers has their own unique IP address. So when the root server receives the query for the IP address for yahoo.com, the root server is not going to know what the IP address is. But the root server does know where to send the resolver to help it find the IP address. So the root server will direct the resolver to the TLD or top level domain server for the .com domain. So the resolver will now ask the TLD server for the IP address for yahoo.com. The top level domain server stores the address information for top level domains such as .com, .net, .org, and so on. This particular TLD server manages the .com domain, which yahoo.com is a part of. So when a TLD server receives a query for the IP address for yahoo.com, the TLD server is not going to know what the IP address is for yahoo.com. So the TLD will direct the resolver to the next and final level, which are the authoritative name servers. So once again, the resolver will now ask the authoritative name server for the IP address for yahoo.com. The authoritative name server or servers are responsible for knowing everything about the domain,
So what's important to understand here is all this traffic that's going around, right? And just as the author of this video previously neglected to mention PAT. So PowerCert was the YouTube channel. We were talking about how NAT works. He didn't really describe PAT. He's missing something here. The client first looks at its own hosts file before it looks at its own DNS cache. If it doesn't find yahoo.com, then it asks the resolver. The resolver looks at its own cache. If the resolver doesn't find it in its own cache, then it goes out to the root server, which is the dot server. So every fully qualified domain actually ends with a dot, not a .com. There's another dot on the end. A proper fully qualified domain name statement includes the final dot, right? So the resolver says, hey, I got to find yahoo.com. And this one says, I don't know where yahoo.com is, but I know where the .com is. So it says, here's where you find .com. You go to .com and you say, I need to know where yahoo.com is. And it says, well, I don't have the information on yahoo.com, but I know where Yahoo is. So it sends the information back, and now the resolver goes to the primary authoritative server. So an authoritative server knows everything about the domain. The primary zone of records is read-write capable. The secondary servers, there are secondary zones that are authoritative. Those are read-only. When you think about the internet and how vast it is and how great the number of DNS transactions that are happening, there are many multiple copies of that DNS zone. A zone is the domain, so the name zone and domain are kind of synonymous. The zone for yahoo.com, you have a zone called .com on the .com servers, the top level domains. You have a zone for yahoo.com on the yahoo.com server. If we had employees.yahoo.com as subdomain, then there would be a separate zone for that because it's a separate domain, right? So when we say domain, you can break out domains down through multiple levels, through .com, through the primary level, then the secondary or child domain. You also call these parent and child and grandchild if you have smaller and smaller domain breakouts. The important thing to remember is how this process works, because hackers love to get in the middle of this and send you the wrong information. And that's one way they get you to go to their online banking website instead of the real online banking website. Any questions? I want you to watch this video over a couple of times because there's important stuff in here.
Includes the IP address. They are the final authority. So when the authoritative name server receives the query from the resolver, the name server will respond with the IP address for yahoo.com. And finally, the resolver will tell your computer the IP address for yahoo.com, and then your computer can now retrieve the Yahoo web page.
So that address for yahoo.com is stored in the cache, the active memory of the resolver DNS, because it's not just this one client that's looking for yahoo.com. It's likely that 100 other people are going to be looking for yahoo.com. So if it looks to the cache on this resolver server first, then the process happens a lot more quickly. The significance of this is if you want a smooth, fast, stable network, you should have your own DNS server on your network to do this right here. If you could, you should run a small virtual machine and have it at your house. In fact, there is a project out. Does everybody know what a Raspberry Pi is?
Yes.
Okay. Did you know you can set up a DNS server on a Raspberry Pi? And that DNS server can be rigged to block ads. So while you're on YouTube or you're streaming media, you get all these ads. It's called Pi-hole. So it's really important to understand what this baby does. This is the lookup function. That's the one side of the coin. The other flip side of the coin are the servers that host the domain records called zones. They're authoritative for, okay, where's the web server? Where's the email server? Where's the database application server? All that kind of stuff, right? Let's stop there. I want you to watch this a couple of times. There's good information. Just remember the one piece that he misses, that client starts by looking at the host's record. Here's what we mean by host's record. Inside your Windows machine, inside the Windows directory, there is a System32 directory. There's a drivers directory. There's an Etsy directory. And inside here is a hosts file. It's going to look to see if there are any entries in your hosts file, and in most cases, the entries are empty. But a hacker can go in there and put in a DNS, an IP address for a given domain name or a host name, a server name, an entire domain name or a server name. And now your client is always going to look at this, no matter what's in the DNS server, no matter what the zone says out on the internet, it doesn't matter. Hackers will set up entries in your hosts file, and this is one way they hijack your clients. It's also one way you can secure a network to make sure that you're always looking at your server and no one else's server. So this is both good and bad. having access to the host's file and using it intentionally for good is a best practice. Leaving it unprotected so hackers can inject stuff in there is bad. In the video, you saw the resolver. One hacker method is to take the cache in the DNS resolver and poison the cache. You don't have to poison the records back here. These are temporary memories. So if your DNS resolver servers are poorly secured, a hacker can change the temporary information in here, and that's much less protected than the permanent information out here. Your online bank has something that's rock solid here. Your local internet service provider has something that's just, I don't know, temporary. And you know, people browse, so they replace those servers all the time. They don't really care as much. This is where a lot of vulnerabilities occur. Are there any questions about how the DNS, so this process of looking first to the root, then to the top level domain, then to the authoritative server and back, that's called recursion. Any questions about that?
No questions.
Okay. So we've covered the trace, the steps that a client uses. Just remember that it goes first to the host file, the host's file, then to the local cache, then to the server cache, then it does recursion. In terms of DNS best practices, when you set up a server, what I'd like to do is take you to some screens where I have a DNS server set up. Can everyone see this screen? Can everyone see this?
I can.
Okay. So this is a system called Virgo, and it's running on the UVI campus. And last year at this time, we asked every student in 243 to design their own domain name, your own custom domain name for whatever personal interest you might have, or family interest. Maybe you want to host a bunch of resources for your extended family, and every year you have 2 very large family reunions. Or, you know, maybe you have a business, right? The point is we want you to come up with your very own domain name. I came up with a notional domain name called groovy.net based on uvi.net. So uvi.edu is the official public domain, but I wanted to create a second one to do cool stuff with hacking and tech for our computer clubs and so on. I put a GR in front of it, and I tacked the .net on the end. This zone, Virgo, is the authoritative server. It's the primary DNS server. I can create copies of records that associate names with addresses. If you've ever seen people type in www, that's called an alias or a CNAME. So when people type in www.amazon.com, that www is also a record that's set up in here. DNS also carries MX records. Those are mail exchange records for email servers, and SRV records for server application servers. DNS is also used, and this is really important to understand, for internal private corporate domains. You can have a domain. Well, let's go full screen here. You can have a domain, and meaning you can have a corporate network infrastructure configured And Fortune 500 companies and government agencies have this. What you're looking at is a domain controller. It's called Polaris. And I'm going to get on here and show you DNS is a critical component of corporate and government networks, internal ones. There are private domains. So there's probably a private domain called uvi.local. In this demo, though, I have the groovy.net domain. And what's important is that domain controllers, all of the records for the important servers and systems and databases and network equipment and all that, it's stored in records on this system, right? And so I want you to understand that there are public domains on the internet and there are private domains that are internal for company networks and organization networks. And it's important to set up two separate servers for this. So I have a DNS server on my domain controller. And what's important is that you configure those servers not to forward, not to go out, except to another server that you own. So the internal ones should be limited. They don't do recursion. They can't go out to root. They can't go to the root servers. You want to prevent them from forwarding requests. So you want a separate DNS server that you control to do all the recursion, all the resolution. In the video that we saw, that one resolution server is the one that you own, that you safeguard, that you protect. But your domain controllers that are running another flavor of DNS called Active Directory Integrated DNS, it's private, it's internal, it's very sensitive. It tells a hacker where all the keys to the castle are, right? Where's all the finance stuff? Where's all the sensitive information? We're going to separate these two DNS roles, meaning we're going to have a separate DNS server for resolution. And then inside our network privately, we're going to refer out to that resolution server, but we're not going to let our internal DNS servers go out on the internet. They are not allowed to use forwarders or routes. They can't go out on the internet to use the root servers. That's a best practice. Okay, that's called split DNS, where you separate the two roles and you have separate DNS machines that you control more tightly, and that way the hackers can't get at it. Does anyone have any questions about best practices?
No questions.
Okay. Let's see how much of this we can finish. All right, so we talked about split. Bind is Linux. So when you have DNS running in Linux, it's called bind. And one best practice is to have separate DNS servers that run Linux using bind. In other words, don't just put all your eggs in one basket. Have different types of servers that do DNS and different operating systems that run those DNS servers. So a best practice is to mix, and the primary server should be one type of operating system. The secondary servers can be another type. So if hackers get into one, they can't corrupt the other. Another recent thing is that we secure and encrypt DNS record exchanges. Now, one thing I wanted to point out was that when DNS servers are updating each other's records, they use TCP. When clients are trying to find a resource by name out on the internet, they're using UDP. Let's say that again. TCP is used between DNS servers to exchange important records about which resources are found on which IP addresses by name. So when servers are updating each other, they use TCP, a guaranteed connection. And in the best cases, they encrypt those records. That's DNSSEC. When clients are looking up information about where to find something by name, they're using UDP to connect to the DNS server. They're not using TCP. Are there any questions about how those two different layer 4 protocols are used, one for server and one for client? Do we have 2 more minutes to show you how to resolve DNS errors? Can people sit tight for 2 more minutes so we can cover troubleshooting?
Sure. Yeah, that's fine.
I can.
So basically, to resolve DNS errors, if you're trying to find something and it says host not found, name, oh, this name doesn't exist, right? The first thing you want to check is your host's record on the client to see if there's something in there. Because if there's something in there, if a hacker put it there, you will never find what they're hiding their tracks. A lot of times they're doing something really nasty that way. You want to clear out the local cache and the server cache. And then if you want to do recursion, you can use NS lookup, okay? So how do we do this simply? Well, I showed you how to access the host's record. You go into the folder into Windows, System32, drivers, Etsy, and then just open up hosts and look at it. And if there's an entry in there, if there's an entry inside that that isn't remarked out, then you need to see what it is, and that could be your source of error. In terms of resolving the local cache, if you open up a command prompt and you on the client, if you type in ipconfig flush DNS, sometimes when you're looking for a named resource, if you get a negative result at first because the DNS server is down, or because the DNS service was blocked on a firewall somewhere along the line and you reattempt it, it stores the negative results. So when you try to find it again, you have these errors in your cache. It'll say, oh, no, we've already been there. It doesn't exist, right? A lot of times there's just a hiccup. Put another way, if the power drops and a server dies for a second, when it comes back up, it's available again. But your cache says, nope, there's nothing there. So it's going to continue to tell you that it doesn't exist. You have to flush the DNS with that simple command. On the server, it's even easier. You basically select the server, and on the server, you right-click it and you clear the cache. And then you select it again and you restart the service. A lot of times when you make new changes, the changes don't update. So you have to restart the service in order for things to update. Then support tells people, okay, go ahead and try it again. And they're like, no, my browser still can't find the web server. Well, that's because you've cached a negative result. So you have to flush the DNS cache again, right? So it's not uncommon to have to flush a DNS cache multiple times, right? There's a whole tutorial out online. I'll put a video link out there for NS lookup. But basically, when you use NS lookup, you can look at specific servers, resolution servers, and authoritative servers to query directly for the records. So in other words, you can take a direct flight and see where the breakdown occurs using NS lookup if it comes down to that. So you can, that's how you follow the trail of error out on the recursive path until you find the problem. Now let's talk a minute about your other solution. You're going to come up with your own domain name. I'm going to set up your zone on Virgo. So when you're completing your second solution, I'm going to send you a survey link to give us a time. We need 30 minutes. So there's a 2-step process to complete your solution. It's actually a very easy solution. Have I posted that yet? No, I haven't. But there is a second solution for module 3 where you create your own domain. You're designing and implementing a custom domain. We're going to pretend that you're Jeff Bezos or you're Mark Zuckerberg, and you've come up with a really cool idea for a product or a service. You want to put it online, and you come up with your own unique domain name. I'm going to post this solution as soon as we clear for the class, but basically, the first step is for you to design your own custom name. And then you pick a time where you and I can go out onto the server, and I set this up. And once I set it up, you're going to clear your own cache. You're going to change your DNS setting on your system. In that half hour's time, you're going to change your IP network settings to use this server, Virgo, as your DNS server. And then you're going to open up a web browser. And when you open up your web browser, let's say that I create a domain name called snurkle.com. It just seems like a weird name, Snurkle. Once I have that going and I've cleared the cache and I'm using Virgo as my domain name server, I'm going to go to a web browser and type in snurkle.com. And when I hit enter, you're going to see a web splash screen. And that's what you need. That's the screenshot you need to turn in for 5 points of credit. Yes.
I gotta leave. Sorry.
Okay. So you can't stick around a few more minutes?
Oh, just a couple more minutes.
Yeah, we were going to talk after the class ends. We're right at the end of class. So does everybody understand what we need to do here? The first thing you're going to do is send me your custom domain name, and you'll respond to the link to tell me what's a good time to get online. We'll share the screen, and then you're going to use your own laptop to connect to a web server with your new domain name. Any questions about the second solution?
No question.
No
Okay.
question.
Okay. Well, that concludes our review of DNS. I'm going to go ahead and stop the recording.